ഗസ്റ്റിലാണ് നമുക്ക് കുഴപ്പമൊന്നും ഇതുവരെ. ഹലോ 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 ബഷീർ ഹലോ ഹലോ ആ ബാക്കിലുണ്ട്. ഓക്കെ. Yesterday, I was കിട്ടുന്നുണ്ടോ? Start the presentation. You make it in that mode, na? I kept here only, 18 July. After the interview, share. Correct. Side mark. Good afternoon. Today we have an esteemed speaker with us, Dr. Siddharth Shankar Das. We have long association with Dr. Siddharth when he was doing PhD. That time we used to visit Galangi, the first ST radar which is established under ISRO in Tirupati, near to Tirupati, Galangi. 53 members immersed radar. This was where stratosphere proposed radar. He did he did his PhD there. That time we used to travel from here during some cyclones and all when they are passing by. I used to go with some of the research scholars here when I was doing the MSc. So I just assist them just to travel because we have to stay there in the night to take the observation. Similar to what we are doing here, our students are taking night observation, taking part in night, taking observations during night time. So from that day onwards, we are collaborating, and after that, we have installed our STRadar in 2016. And still, I would say that Dr. Siddharth is one of the main user of this our radar. Not only the main user, he is making maximum out of this radar. So I would say like that. And he is, in that way, he is contributing to the development of new technology development and new way of extracting atmospheric signals through our radar. So our radar is unique radar, 205 megahertz. It has both its own advantage and advantage, mostly advantage compared to other frequencies. So without much delay, he's scientist GSG in space physics laboratory. We want to apply space PSSC. So he has maybe more than 70 peer-reviewed journals and he's in number of many academic and research committees. So without much introduction, so I warmly welcome Dr. Siddharth. And students, we have here embassy first time and there some students. So first time students, they are just going to start their class from next week onwards. So consider them as very beginners and maybe you can interact with Siddharth, get your doubts clarified. Welcome.
Thank you, Professor Abhilas, for a nice introduction. And he was saying that we have a long affiliation, almost more than 20 years. We have spent our work. And many things I have learned in atmospheric science from Abhilas. He's a meteorologist and I belong to a physics, belong to a digital and electronics background. So there was something different and many things I have learned because we have a knack operation of radar and all. So I want to say thanks to the Kochi University for giving all the facility, whatever we are conducting experiment and everything. And my student is also here with me. So I will keeping actually when Professor Abhilas was telling me that we need to have some type of talk as well as like a discussion, and it is like MSc student. So I am not going to the so many research. I am going to show something fundamental. What we can do with this radar because this is one of the very good radar because I am working with many radars in India. We have a network radar which I will be showing you. And you can see that these radar having a much more capability and it is uninterruptedly having more than 7 to 8 years it is working and it is perfectly the spectrum data and all what we require. So as I say, I belong to the space physics laboratory where I am in the middle atmospheric dynamics branch. I am going to give dynamics. So today my presentation this is in online mode. So I will be talking about the history of the radar, how the radar was developed and all. Then Indian aspect and the present scenario, how it is like that. Why we have in India and how many radars are there and why it was installed at the particular place. Then some fundamental of the radar. I assume that most of the people who has done the BSc may be having physics, so it will not be much difficult for to understand the radar system but not much going into the electronics, but I will show the overall the blocks and how it's work and then what type of things we can do with the radar. So that's why then other is like Earth atmospheric process. I will show one slide where the different processes of the atmosphere is, especially the lower atmosphere. Then how you can probe with the radar because this is one of the unique instrument where uninterruptedly you can do because like you may be knowing about the IMDs launching balloons and all, but that is again at 2 times and you cannot get the continuous measurement. Then some special experiment because earlier during our student time this type of radar was not available. This is active aperture radar. Some special experiment was conducted. How you can do that experiment because then what we can do with this MST or ST radar in the future. So this is my outline to not to get confused because this is like some fundamental for the MSc classes and 1 or 2 result what we did with the existing radar system. So as I said, like most of the people are from the physics background, so it is not that easy, difficult to understand. It's slightly easy. So you know the Maxwell's 4 equation. All we know that the 4 equations. So this is in 1831 and all. It was formulated this classical theory of electromagnetic by the Maxwell. And then the Hertz did the experiment. You might have seen the TV antenna, but now you may not be having. Earlier during our time, we have a dipole, and you have some spark. There will be a space. There will be a difference between that one. So you like when you do a sparking, there will be a electromagnetic waves will be generated. So this is 1857 onwards, this experiment was conducted. So this was the basic when the radar system, before development of the radar system. Now this like radar is like, you may be knowing that radio detection and ranging. Actually, this is electromagnetic. You send the electromagnetic wave, it will hit to the object, and depending upon the radar cross section with the area where it is interacting, the return signal will come. So you can get, in principle, there's time, the space and time, the movement of the particle or the body, and you will be getting back the signal in terms of the Doppler effect. So then the Marconi first invented the radio, that that's in the 1901. Then Gauss, then this is actually a sequence of the radar. So then the Gauss, again, he has proposed some theory, then electromagnetic waves will be generating and electrical current which generates the electromagnetic waves. Then if you come to the last one, that like radar development as the root of research above the electrically conducting layers in the atmosphere. So you may not be having radios now, but earlier there was the radio which is having FM, AM, the medium wave and all. So at night time you will be getting many stations, many radio stations, but daytime you will not be getting. So that was why such things were there, because when they transmit electromagnetic wave, daytime you are getting the radio signal, less radio signal, whereas at night time you get many much more because of your earth radiator, the curvature of your earth. So there it has to transmit and it will hit to the conducting layer and it will come back. So that's was their assumption. So this type of layer will be there or not. Then this Kenley and the heavy side, actually what they started, that after the Marconi has done the radio thing, so they independently thinking that there may be something which it is transmitting, and whether that type of any layer or any object is there which is transmitting the signal. So then they designed some experiment, but then it was not accepted. Then the probing of the ionosphere, the first pulse radar experiment was conducted. This was the by two in 1925. They tried to send the signal, and they are thinking that there is something which is reflecting back like a mirror at 100 to 180 kilometers. So this is the first starting of actual radar system. Because when somebody is talking about radar, people may be thinking that radar system is because of the World War. Then we came to that world, from World War it has come, but actually this they wanted to see some layer structure. Then this was the development of the radar system. Okay, it can go and hit to some ionized layer and come back. Then Appleton and 1926 they determine a layer of the reflecting layer. They confirm, yes, this type of layer observed. So this is actually all is related to the ionospheric thing. So if you see the sequence, like how they detected the radio waves from an atmosphere, that is the conducting layer. Then after that, there were the medium frequency. I will come in slightly detail in that one. Then high frequency radar. Then UHF wind profiler, which you are having here, one VHF profiler that is actually starting from 30 to 300 megahertz, that we call as a VHF. That I will be showing one table there. So this is what actually the development of the radar system happened. Then the first radar over the world was at Hicamarca. Actually, it is starting with the JIC, but we call it as a Hicamarca. That is in Peru, near Peru. And 1974, the Woodman, he is the man behind that, and he developed this radar system that is over the tropical region. Then if you see our Indian scenario, there is a place called as a Haringghata that is near to the Calcutta, being almost 45-50 kilometers from the Calcutta main city, where the S.K. Mitra, he is the person in 1930, he installed a similar kind of things like ionosonde, which he observed the ionosphere. Continuous measurement was there. Now also it is there. Now a new radar system has come up there, that is Calcutta University stratosphere troposphere radar, similar to your radar, but in the different frequency. It is working in the 53 megahertz, whereas your is 205, 206, you are having that one. Then NOVA developed the network of radar. So this was after seeing this this UHF VHF radar over the location at Peru. So they started developing this radar system to get the wind profiling, because like radio sonde, you launch a radio sonde, you'll be getting a wind profiling. But radio sonde can burst at any height, radio sonde can travel to any direction, but radar will be probing exactly perfectly, doing the probing the atmosphere in the vertically. So this was like worldwide how the radar was developed. But what about our Indian first radar? That is a Indian MST radar, which is Gadanki, where we need to have a lot of experiment there. So and that was designated during that time world's second largest radar after Peru. That much big antenna was there. 130 by 130 meter. It was a square array. I will show you one picture there. So then program internationally, that is middle atmospheric dynamic program, started. So on that basis, they wanted to have the requirement of the radar system. So where to install that radar? Because there was no other than Peru, there was no radar system which was installed in tropical region. And you know that Indian monsoon is one of the most important thing and globally studied phenomena. This phenomena was, so they proposed a radar, and it was the student of SK Mitra, that is an AP Mitra. AP Mitra is a student of SK Mitra, and he was the leading at that time that IMAP program. And IMAP was an international middle atmospheric program. And in that one, they proposed a radar system which was installed at Gadanki near Tirupati. And in 1990, they started in ST mode. Then 1992 onward, they operated in MST mode. MST means, ST means stratosphere troposphere mode, and MST means mesosphere stratosphere troposphere. Because that radar is very, very powerful. It was 2.5 megahertz, and area is very big, so it can probe the mesosphere also. So that was the intention during that time. And 2015 onward, before that, it was in normal radar. Then 2015 it was advanced, and it is similar to kind of your radar. Your radar was the first radar which was having active aperture, and it was operating. This was operating in all direction. You can do like a, you can move the beam in all direction. All radar was not having that capability. So this is a worldwide. This is the radar which I was talking about, Gadanki, and this is the pure radar. That is actually 300 by 300 meter, very big radar. If you see, this radar is 130 by 130 meter, and this radar is 300 by 300 meter. That is very big radar. Then apart from that, there are a lot of other radar system was developed, China as well as the RT, and many places it was developed at that time. Now, what is the present scenario in India? We have this is actually documented one. That's why I'm presenting, because otherwise there will be some radar system. ISRO is also having one more radar system near to Shar, but those things are not used for the academic purpose. That is for the launching purpose. So that I am not putting. So these are the four radar: Gadanki, Nainital, Haringata, Kochi, and Guwahati. So these radar are now in the perfectly working condition, and Gadanki and Haringata, these two radar, this Calcutta radar, these two are working in 53 megahertz. I will tell why a particular frequency is required. And these all other radar are in the 200 range, means 205, 206, 202, like that. It was there 200 range. So this is the locations of all the radar system like Gadanki, Haringata, and all, and different frequency which I was talking. And other detail I'm not taking. This is just I kept from some other slide. So these are other details are there about that radar system. Now coming to the technical things, how a radar work. As I was saying, you have a transmitter, you have an electromagnetic wave. The wave will be generated in the transmitter, and it will be transmitting through an antenna. It will hit the target. Target may be moving or not, and you will be receiving. So what will happen? You send in a constant frequency, you will get it with a Doppler shift. So then that Doppler shift will be measured, because then you can get the velocity is equal to distance upon time t. In that terms, you will be getting the velocity of an object. So you have a two different mode of operation of radar. There are two types of radar, you can say. That is like a pulse radar, and one is a continuous wave or the Doppler radar. So if you see the pulse radar, it will transmit the pulses, energy pulses. That is a packet of one pulse, then stop, another pulse, then stop. So it will measure the delay of the time delay from receiving the echo, and it will measure the range. What is the range of that one? But you cannot get the velocity at that time. The motion of the target cannot be known, how fast it is moving. But if you have a Doppler, then in the principle of the Doppler, simple Doppler things, because there is a Doppler shift, you can calculate the velocity. So if both the radars are combined, this pulse and this Doppler, you become a pulse Doppler radar. That is what actually you are having. In Kochi University, you are having pulse Doppler radar. Now, why a particular frequency is used? Actually, if you see in Earth atmosphere, there are different sizes of these scale sizes. You know about the parcel. Different parcels are there, and different sizes will be there. So these sizes can be probed by your, because it is depending on a wavelength. You are depending upon your scattering. So what type of if you, this is a height, for example, 0 to 90 kilometer, and this is the scale size in the atmosphere. So if you have a frequency, this frequency you can observe only up to 20 kilometer. If you have some higher frequency, you can observe, depending upon your frequency, your height coverage of your radar will be increasing. So actually, only little advance is there. There is a Kolmogorov spectra. In that one, when the small energy will be forming, then there will be cascading of energy, and another will be dissipating. This you will be studying in your when you are going to the, I think, second year. There is a Kolmogorov spectrum is there, that turbulence thing. So this is how a radar is designed, because you cannot randomly choose the frequency that I want 50 megahertz or I want 200 megahertz. So this is how what type of study you want to do and which location you want to have. You have to go for this type of study first. That is turbulence thing. Then this is simple frequency of the radar, different frequency. Like I was telling that VHF radar, UHF radar. UHF radar is a wind profiler which can probe in the lower atmosphere up to 1 or 2 kilometers maximum. But VHF radar, it can probe from the 300 meter to up to 20-25 kilometers you can observe, which is our Kochi University radar is like a VHF radar. Then you have a L-band radar where you can talk about the precipitation, rain and all. You can talk about that one, but clear air you cannot talk much with this radar. Then there are S-band, C-band, X-band radar. These radars are like a Doppler of the radar you might have seen in airport or near to, and I think Kochi it is there near to the seashore. You can see a dome type of thing, football type of structure. Actually, inside there will be antenna. So different radars, I think it is S-band radar, and it can probe up to 400 kilometers, but it is not like a clear radar. It will be probing like you have precipitation, cloud, that type of thing, thunderstorm, you can get. X-band radar, it will for the only for the short up to 100 meter, it will be taking seeing, and it is similar kind like your Doppler of the radar, and you can get the your rain, precipitation, all this mapping you can do, because you cannot keep on having your precipitation measurement all over the places. So this radar will work out. Will be sitting in one place. You can probe the entire area, how much precipitation happens, because you can see that during the mitigation time, you are flood or something will be happening. So how to find out that where the more rain is happening? This radar will give you a good picture of that one. Then you have a K band, KU, KA, and W band. These are the mostly in the space bound. It will be there, but some W band radars are there in IITM and all. They are because they have many of the radar they are having, but not the UHF. UHF they have, but not the VHF radar. Then for the ionospheric study, MF, HF, and ionosphere, those radars are used in the very this frequency 2.5 megahertz or 3 to 30 megahertz. These ionospherics and all. This for the ionospheric mostly. I think W band Madhu purchased initially W band, but now I think they don't have W band. That was in Mahabaleshwar. They have for some time they observed. K and Q band, K and W band. I think no. I think they Madhu proposed that one, but they didn't get. This is actually in the our satellite you are having that one, that 94 gigahertz. But I think now SPL they have proposed with Balasore, that is a multi-frequency radar. So that time I think they have proposed this radar. So now in the some radar jargons are there, because when you talk about some radar person, so he will be talking about pulse width, Doppler, wavelength, interpulse period. Because when you design some experiment with radar, you cannot not like a fan, switch on, switch off. You cannot do like that. So you have to design the experiment in a different way. So these are the different terminology. I will be just talking about one line about each terminology, because mostly I prepared this slide for like a student for the JRF thing. So that's why I will be talking in that terminology. So pardon me if I am a little bit more basic, I am going. Okay. So like you have a different scattering, because all radar, you switch on the radar, you cannot get the signal, because there are the different scattering mechanism there. Like a Mie scattering, Rayleigh scattering, optical scattering, and Bragg scattering. These are the different scattering, and I have listed here like LiDAR, weather radar, hard target, and the clear radar. This Bragg scattering is the radar. I will be talking much on the Bragg scattering, where our radar, VHF radar, like Kochi University radar, MST radar, or Calcutta radar, all these radars are working on the basis on the Bragg scattering. So this is a different range where you will be getting, and you may be knowing about because totally depending upon your radar wavelength, the target size and the radar wavelength. So this will be defining that whether it is a Mie scattering, Rayleigh scattering, or optical region. So this is different type of scattering when you talk about radar. And when you talk about the VHF clear radar, it is a Bragg scattering. When you talk about the weather radar, it is a Rayleigh scattering. So this Bragg scattering, how you will define, like you know the Bragg lattice, right? In your material science, you might have studied the Bragg lattice. So it will be always having a lambda by 2 differences. Okay. So when it will be when your signal is transmitting, it will hit a layer, and Again, the second layer will be like a lambda by 2, the second layer. So all these layers will be coherently integrating. So that's why we will be calling as it like a turbulent or the backscattering. And if it is like a perfect reflector, like if you have a mirror and you switch on a light, like a torch light, if you hit, it will come back. Exactly. But if you did the thing, it will not come back. It will go to some other state. So that will become a perfect reflector. So this is what actually you call as a like a Fresnel reflection. But scattering will come if your size is like this. So near is the ball, any direction if you lead, it will be like a tangential line. If you it will be perpendicular to the return signal. So what will happen? Any direction you lead, you will get the signal back. So that will be like a scattering. So that will be a Fresnel scattering, Fresnel reflection. Fresnel reflection will be like a very perfect mirror. And this refractive index, actually, you know that atmosphere having a temperature and humidity, and this refractivity, this is what you study in your material science, that is the same thing, refractivity, that depending upon temperature and your water content. And this gradient, if there is a gradient in the refractive index, gradient in the atmosphere, then only you will be getting the return signal. If it is a well mixed layer, you will not get the signal back. So that is how you are getting the scattering back from your atmosphere. And another scattering, this is a coherent, whatever I told the Bragg, and another is incoherent scattering, because there are two type of radar. One is a coherent radar, because where your phase is locked. We talk in terms of phase log, means when we know what phase we are sending, and when it come back, what phase we are receiving. So that only will be taking. And incoherent, it will be like if you want to have a electron temperature and all this, like it's a Thomson scattering. So that type of things will be only for ionospheric study, not in the lower atmosphere, Thomson scattering. So generally we don't consider this one for our studies, but for the Bragg, only coherent we will be taking in that part. Okay, so as I said, like this is the Bragg scattering, Fresnel reflection, only one layer, one single layer, and Fresnel scattering, multiple layers, or you have isotopic type of things. So you'll be having a maximum type of signal return back from this type of Bragg scattering. Now, when you send a signal in a radar, actually this is known as a pulse signal. So you have sent a pulse. This is actually a pulse. Then you switch on, because your radar cannot be switched on continuously to send the signal. It has to, because it will heat up. So you have to switch on. The switch on is not manually. It is everything is done electronically. You send the switch on. So this shows you are sending the energy. Then after that you switch off. It is only in the receiving mode. So you will be receiving only the signal from different height. You send a pulse, then you start receiving. So that is actually known as a pulse width. So when we design a radar experiment, we define how much energy we should send. That is a pulse width, and how much time we should have a signal back. So when you send a signal, it should be sufficient time to switch off all your signal which is going to die out. Then only you will start getting. Otherwise, what will happen? From if you send a signal, then after the immediately send a signal, that from which signal you are return you are getting back, you don't know. So that's why you require more IPP, that is known as the interpulse period. Means distance or time difference between the two pulses. That is what actually IPP we call as IPP. So when you are designing, that much will be there. When you're designing a radar, then how much the duty cycle, that is also actually a manufacturing fixed thing. So how much duty cycle is there, means how much time you can, your energy sending and energy stopping can be done, because how much your radar can sustain. So that is called as a duty cycle, because this terminology, if you start working on radar, you will heard about this terminology every day in that one. Then how much height coverage you can do. This is your IPP, because you know when the electromagnetic signal is sent, you will be that speed of the light 3 to 10 to the power 8 meter per second. So it will be going and coming back. So then you can calculate that how much time will take from each layer height. That is actually depending upon your velocity of the light. So that's why we call as a how much height can coverage. That is depending on IPP. How much time you switch off, that many height will be coming up, because one height, second height, third height, like that it will be. So as much as time you need, you will get something much more. But just by the time reach to certain height, your signal will be very weak, because energy will be dissipating. So this is how actually we call as like a maximum coverage height, and we require to have that one, and how much minimum. This is depending upon your radar designing, like a blanking switch, we call it a blanking switch, and pulse width. So that will be there. And you see, one signal is sent, then you will be getting the return signal. The red line is a return signal you are getting from that one. Then when you design a radar, you require to have if you send a signal, suppose you send this much amount of energy, then you will be getting from a maximum from some range. But to make the range double, you require to make the power 16 times. It is not that if you make a double, you will get a double return signal. You will not get. You will require 16 times. That is because of your radar equation. So this is the radar equation, and we have a like a gain of the antenna, how much energy the gain of antenna, and the R max. That is what I was telling. That is because R to T to the power 4, R max to the power 4. So that's why when you require the return signal from double height, that you require 16 times of energy. So your radar cost and everything will be increasing very high. So you should have some optimum how much you can spend money, then that much return signal you will be getting. So finally, you will be getting the signal to noise ratio, power and all. And then after designing the experiment, so what exactly we will be getting one by one, I will show you. This is a radar cross section, because depending upon your target size, suppose for example, when aeroplane is going, okay, that is a hard target. So you will get a very nice signal. But if you have a cloud, or if you are having some air parcel, so you should have a minimum radar cross section to reach it. From each day you may not be getting. So you require minimum. So that is why radar. This is very, very important parameter we require to have that one. Otherwise, we on with that basis only we can design the what is that radar when you are initially installing. So these are the different formula. I'm not going in detail in that one. Then you may be knowing that this radar will not give from the surface. So your radar is installed surface, but if you launch a balloon from surface, you'll be getting from the surface till the balloon is bursting. You'll be getting the wind profiling and the temperature. But radar will not get that. That is because of your far field zone. Actually, the radar beam, each antenna is radiating, and it's like a hydrogen it will be forming 111. Then there will be 480 and a well-defined beam will be there. The 480 will be having. So from the distance when it will be forming, maybe here it is a 315 meter or something. Below that, that is known as a near field zone. You do not have any signal, well-defined beam. Above that only your beam is forming. So from that height onward only you will be getting the signal. So that is actually far field and near field zone. Then when you design a radar, because where to install the radar? Because if you have a hill nearby, then there also a problem. And then you where to install, and you should not have, you should be free of that. That's why we call it a noise survey. We'll do first the noise survey over that, whether that similar frequency is available over that location, and we will be designing a radar. So when your radar is of say, transmitting a beam, you see there will be a black lobe. Okay, so when your radar is you can see only antenna, but you cannot see the beam is tilting like this. We are tilting actually beam. So it's like a balloon structure you are having, no? So if you tilt your beam, this balloon structure also will coming up. So you will be getting signal from one direction, you will be getting signal from other direction. So that you have to eliminate out. That is known as actually you are suppress the clutter. We call it a side lobe suppression, and side lobe, that is actually all these small things are known as the side lobe. It has to be suppressed as much as possible from the main lobe. This is actual I think this is 1.22. Okay, this is over Garden Ki, I think. This was the one radar we designed. How much it will be there? Suppose this is your illumination of your radar, then you have a beam width, because when you see the balloon when it is launched, it is like a single point. But when the radar you are illuminating, it is you are illuminating like this. So all the scatter from here as well as here you are getting the signal. We assume that the scatter which is reflecting having the same characteristics over that one. So this beam width will decide, because your beam is sending, you are sending in that one. You are thinking that it is a homogeneous distribute, and this is a power. It is in dB, so the power by 2, half of the power. When you beam is there, your power is maximum. Then half of the power, then angle what you are getting from the beam. So this is the beam width, which is very, very critical. I think here is 3.5. I think 3.5. 3.5 is 3 degree. So it is a 3 degree. As narrow. Actually, I want pencil beam. Pencil beam is one like a one straight line, which is not possible. So as much as your antenna will be increasing, size will be increasing, your beam will be decreasing. That is what actually this designing has. So for like I was telling, if you tilt the beam, you see there is a 2 signal you are getting up. Actually, we should have 1. Then we don't know from whether you are getting from this beam or from the other beam. That's why we have to design the radar in that way that when you tilt the beam, it should not lift up. So that's why they will do some fencing also, so that the side lobe should not go, and that also is there. And that fencing should be again lambda by 16. Now, as I was telling you, this is simple a Doppler effect. If you send a signal pulse, you will be getting like this. Okay, one radar is there, and if you are moving target, so if you hit now, if you have a just shift of the Doppler shift is there, so you can find out the velocity. Suppose there is a Doppler shift, you can find out the velocity in the terms of the wavelength. How much shift is there? Then that much, because that much distance it has traveled. So that is actually where we'll be having the pulse coherent radar, because pulse coherent radar means you know the phase of your wave and you send the signal, the phase. The phase is locked, you know the phase, then you'll be getting back the signal. Then how much shift is there? You can get it back. What is the velocity? Okay, this is actually, we call this a little deeper. We call as a I and Q, because when you take the raw data, because when you send a electromagnetic wave, you'll be getting some time series. This is not wind information, but actually we require wind information and turbulence parameter. That is what actually we require. But if they digitally, what we are getting is some numbers. That number is like, we will be getting this red line you are seeing, no? You are continuously sending on pulses and you are continuously getting a signal. That is just like, just when you talk, you're getting some signal, right? That is what you are getting. From this signal, you have to extract the things. How you are extracting? So you are getting an I and Q channel, that is we call as a in quadrature, and this will be the actually real time and imaginary. So this is in phase, that is real time and quadrature. So this is I and this is as a Q. We denote in that way. Then once the radar give this I and Q, this signal, what we will do? We will do the coherent integration. This I will tell you what exactly we do. Normalization, window, Fourier analysis, all these things will be processed. After that, you will be getting actually zonal wind. What meteorologists want? A zonal wind, meridional wind, a vertical wind. And this is only the radar system. Actually, what VHF radar gives a vertical wind. There is no measurement of vertical wind profile in anything except the radar. So that's why these radars are so unique. Why we require that type of radar? Okay, so now I told that we have sent one signal. So this everywhere you are getting one I and one Q. Once you send a signal, you get one time series. Again, you send a signal, you get a one time series. That time series, you are thinking there is no change in the, like I there is no change in your air parcel. So in that one, it is averaging. So it will start averaging. That is known as a coherent averaging. Coherent averaging means phase is not changing within that time. So we will average. That is known as a coherent phase. So this is what actually you see when you send a signal, it will be like a noisy, too much. When you start doing like coherent integration, nothing but coherent integration 4, coherent integration 16, coherent integration 64. You see, you got a very smooth line. This is what actually happening in the atmosphere. You send a signal, then you will be getting a smooth signal like this. From there, you can do the Fourier analysis and get all the wind information. So actual radar signal is like this, but we are getting a spectrum. This is actually I and Q channel in time series, and you are getting a signal like this, where from your Doppler shift. Now this is a Doppler. You can see this one, and you can get one Doppler shift in that one. So once you get a spectrum, now so many spectrum you got. Now, if you so many spectrum you are averaging, that is known as a incoherent averaging, because your phase information is lost. Nothing is there. So when you do start doing, you see actual spectrum look like this, very noisy, you can see. But if you do this averaging of multiple spectra, but only the time you will be losing, you get a very smooth spectra, you see. Okay. So because when we talk about radar, the spectra is the main thing. From there only you are getting whatever the output, that wind information. Then you start fitting a Gaussian, because of the spectra is still noisy. You can fit a Gaussian and you can have how much Doppler shift, then how much power. This is a population density. If you keep on adding that one, you will get the power, how much power is there. And rest of the things are noise. So you'll be getting signal to noise ratio. And we call as a zeroth moment, first order moment, second order moment. These type of things are they are in the radar to calculate the UVW finally. And then because like I was telling you, radio sondi you launch one morning, one evening. That is actually 00 GMT and 12 GMT. So you are getting every 12 hours one thing. But here you can design the exaggeration, you can exaggeration everything. Every 2 minutes also, 3 minutes also, you can get one information here. But only disadvantage that you cannot get directly temperature here. You are getting from radio sondi measurement. That is what only you can get only the wind information. There is indirect method where temperature can be derived using the vertical velocity, but very high resolution vertical velocity is required. Now, all this process is done. because these things, whatever I told, this is actually the totally done by a engineering background, and then people will do these things. We may not be all metrologists or our person may not be knowing how are the design done, we can design this, right? But what finally we are seeing is this is the thing what we are seeing. When it was in zenith, when it was 10 degree of zenith, when it was west and south north. This is actual data of Cochin University. Here, this is recent data we collected, and this is you see the profile you are getting, the perfect. Why I was telling means we work in many radar in India, different radar, but this type of perfect clean profile, very few radar. Gadanki radar still give that radar, and this radar is giving, but still sometimes it fails to give in the 14 to 16 kilometer. But here you see, this is one of the where you can get very strong. And you heard about the tropical stellar jet, right? The TEJ, you know, you all are meteorologists, so you may be knowing tropical stellar jet. Very strong wind at 14 to 16 kilometer. It can reach much more than 40 meter per second. This is what you are seeing. You see, this is the height profile. Nearly at 16 kilometer, you are getting 15, 16 kilometer, you are getting very strong Doppler. This is in terms of Doppler. So you have to multiply in terms of the how much zenith angle of zenith angle, then multiply lambda by 2. You will get some 40 meter per second wind speed. You see, this is east, this is west. You see, this is a mirror image, because when you look in one direction, if your wind is coming like this, it will be positive Doppler. But when you look in other direction, it is for the radar, it is going away from the radar. So you'll be getting negative. That's why you got exactly perfect mirror image. This is a normal condition. And this is actually the power in terms, you can see the very good signal up to 20, 21 kilometer, much more than that. So this is actual thing. But this is during the normal condition. But what will happen during the convection? You might have seen that in the month of March, April, May, it was a very clear sky day. Suddenly there will be cloud will be forming and heavy precipitation, downpour will be there. So that type of things, that time no balloon you can launch. Every balloon will burst at 5-600, but you see your radar can go much more than that. And you can see the signal like earlier you were seeing very clean one signal, right? And here you see very broad, red is very big. That means highly turbulent. So you can have that type of thing. You might have when you travel in a flight, you might experience that type of thing. Highly turbulent. Very, within fraction of a second, can fall down, can come up. So that we call as a updraft and downdraft. So this is a very highly applicable. Actually, this type of radar should be there in all metros and all nearby. That's why IIT is planning to have many this type of radar. Where when such system is forming, also we can observe well before that. Because your eye cannot observe, but radar can capture that one, and we can alert that yeah, this type of things are going to happen. So this is mostly by this type of radar you can get this type of system actually. And when it become clearer radar, when it's a cloud, your DWR can detect, your aeroplane have a radar that can also detect. But if it is a clear sky, nothing is visible. If this type of phenomena is happening, you cannot see. Your aeroplane will be going very nicely, suddenly it will fall down by 1-2 kilometer, or suddenly it can lift up to 1-2 kilometer. Because now aviation safety is much more important. So this radar can only see. That's why we call it a theater radar, and like theater terminus CAT, we call it CAT. So all some at the airport have this capability that theater terminus can detect it. So this is what this radar was. This is actual data from the Cochin University recently observed, and you can see two type of thing. One you can see here by this red cursor. Another you can see here. Actually, when it is rain is falling. So it is like it is coming toward the radar. So you will be getting a positive Doppler. So this is actually rain echo. You can see very clearly rain echo. And other one you can see the velocity very high, the vertical velocity. Generally, in principle, vertical velocity is centimeter per second. But when you have this type of phenomena, the vertical velocity may go much more 12 to 13 meter per second. That we have observed in MST. Now, yesterday, we are crunching the data. Yesterday, we saw up to 8 meter per second. We have seen. Ajil was showing me today morning also. It has gone, I think, 7-8 meter more than that. It has gone up to that much. So this type of radar have a capability. So you see, starting from just a noisy signal, how the radar was giving a good signal to you. That is what this is what actually we want. But when you see the starting thing, okay, some noisy, some integration, something was done. But that is mostly done by most of the things by the engineers that we will be doing, and then we'll be getting the output from that finally. Now, because you know the direction cosine ratio and DCs and DRs that you have studied in your mathematical physics or in mathematics. Now exactly use of there, because you have radar in that one, but you require in terms of the component of the wind, zonal and meridional wind. So we have to observe in the different angle. That's why I was telling zenith and off zenith angle. So you can calculate actually the zonal, meridional, vertical. These three wind, we require these three equation, because for having a three variable, we require three equation. So three, this is unknown variable, no? So we require 1, then 2, and 3. Then it should not be 3, 1, 2, 3 should not be. That's why it's known as a coplanar and non-coplanar. It should be like a non-coplanar, the 1, 2, and 3. It should not be in the same plane. Then only we can calculate the UBW. So if you have a 3 beam in the radar, you can calculate UBW. But generally, what we do, to have a least square fitting and all those things, we use 5 beams. Then you are having a averaging, and you get a much more smooth profile from that one. So starting from here you are getting Doppler. You are getting Doppler. You are not getting the wind directly here. From this Doppler, we will be calculating the wind. This is what actually we want, UVW. Okay, now coming to the major phenomena, if you see the tropics, you know, this tropic is a maximum solar insolation over the earth. And then a lot of circulation, you know about the BDC, water circulation, hardly cell, because to make it uniform, the temperature, one is very, very hot and another is very cold. The transport and all these things will be the circulation. Okay. And I kept one figure here. This figure shows that what are the different processes. This is a temperature profile. This is a height. This is a temperature profile you can see. And over the tropics, this is mostly over the tropics because we belong to tropics. So mostly over the tropics, you have a gravity waves. You have then a tropopause. You have a tropopause breaks sometimes. Then you have an Indian summer monsoon, pond layer variation. So this shows that different. And then wave characteristics, equatorial waves, because within plus and minus 5 degrees, you have a strong equatorial waves. You have a QBO, quasi-binary oscillation. 2 years you will be easterly, 2 years it will be westerly. This is very nicely. Then you have a tropical easterly jet. You have a low level jet. Many things are there. Okay, so that's why this type of radar system are most important, because it can have a continuous measurement uninterruptedly, and whether it is any weather condition, actually, whether it is a heavily raining or it is convection or cyclone, you can operate the radar. So this is different phenomena over that one. Now, from a radar, what exactly we got? We got signal to noise ratio. Then we got Dopplers. From Doppler, we are getting zonal. This is actually actual data of Gadanki. You can see it is almost like 25 years of data, average data, climatological data. And you can see this zonal wind, meridional wind, and vertical wind, where you can see. And this dotted are the tropopause height, which is detected. Tropopause height is a height where between the stratosphere and troposphere, it will be distinguished between these. You may be studying in your classes that one. So you can detect from the radar very high resolution. And this is the turbulence. You see, during the month of June, July, August, monsoon month, highly turbulent over that one. This is spectral. This is actual measurement from the radar. Now similar thing you can have from your own radar, from Cochin University radar. Similar thing, you can see that SNR. This is signal to noise. You can see the signal to noise ratio over this location at this time is very high during June, July, August, and it is expected because it is highly turbulent, having a tropical stellar jet and all. And you have a low level jet. You can have like over Gadanki, you may not be having much more, but over here you can observe very high low level jet and all. You can see over this location. Okay, then this is over up to 20 kilometers. That is actually the troposphere and some part in the stratosphere. But MST, as I call, only that is radar which is M. M is written, that is mesosphere, because you can get mesospheric echo, daytime echo. You can get at 12 o'clock to 4 o'clock. There also you can get the wind information like a 65 to 85. So mesospheric echo you can get. Here also you are getting mesospheric. No. Calcutta they got some mesospheric echo. Here you will get daytime. So this will give you 65 to 85. And like our VSS Vikram Sarabhai Space Center, we have a rocket. We used to like this ISRO started with launching small rocket in 1960s and all. That is Nike Apache. Then after that, they have an M100 rocket from Russia and all. So they used to measure this wind. At that time, radar was not there. Once in a fortnight, means every 15 days, they will have a rocket. You can come and visit our VSSC, and you can see now also just to have a heritage, we are sending the rocket from 65 to 80 kilometers. We are having the wind measurement over our location. So that time this radar was not there. So that was, this is only the wind where we can get radar, where we can get the wind information. But now radar is there, and digital radar can also be from 75 to 85 and all. But I think we can try with this radar. If we can get this information also, because this is most important zone where our re-entry of our reusable vehicle. We heard about man mission and all those things. You know? When you launch is not a problem, but when you come back, there will be high friction because you should have all the wind information, and you should have a density measurement and everything, because temperature and humidity information over these locations is very, very important. Mesospheric height. Last time you might have that it was burned and many astronauts was died. This is the reason where. So we require this wind information continuous. So all radar is not giving, but Gazanki radar gives this information from 65 to 85 kilometers. Now earlier, like I was telling, when we are research scholar at that time, we used to operate the radar in, like you can see, like east west. This is the formation, like east west north south beam thing, and only we have this capability. We cannot have like rotating capability like Cochin having. So then later on, when the capability in 2015, it was enhanced in Gazanki, and now all radar having this capability. You can rotate the beam whatever direction you want, east west north south. Then you can rotate like this, and you can get full map. Because when radar is like this, you can see only one. But when tilt, it can go to 7-8 kilometers in the distance. So you can have full coverage of that one. And we conducted many experiments with this radar as well as with the Gazanki radar, as well as Calcutta radar also. And we got a very good result, because earlier assumption was like that. I was telling you, within the radar volume, your parcel characteristics is not changing. But when we have this type of experiment, we could able to understand it is not so. Some places it is failing that one, because some places it is like isotropic scattering, some places it is anisotropic scattering. Different scatterings are there, so that it fails when we do this experiment in the weather normal weather condition. So this is an actual data. You can see how it is like a piling one by one by one. Means earlier we are having only one observation. Now you can see the over the 7-8 kilometer area we can have like a Doppler of the radar. You can have the full coverage of that one, and you can see the wave characteristics. You can see the different colors. Different colors shows the different characteristics. Actually, it is not the same. So it is like a capturing. Earlier we are thinking that if you send, it should be like a red or blue, or it should be common, but it is not like that. It is having a change because of the different scattering mechanisms here. And I think everybody knows the temperature profile. If this is the temperature profile, red color, and you can see the tropopause here. Okay, and from the radar you can see that is very strong. So because tropopause like this, so like a mirror. So if you send a torchlight, you get back. But if you kill the torchlight, you will not get back. It will be less, because that's the actual aspect sensitive characteristics of any radar. So that's why you see one dot only center, and the power goes decreases. So you can detect very continuously very high resolution measurement tropopause. Because why tropopause is that much important? Why I am emphasizing on tropopause? Because you have a ozone layer in the stratosphere, and you are having a highly humid air in the troposphere. Both should not mix, but many conditions we observe that both mix. Because ozone is very good when it is in the stratosphere. That is only good ozone. But that same ozone when it comes to the troposphere is bad in it. So these layers stop. Clearly, the humidity is very, very high over here. But when we have very strong convection and all, it will pump your humidity to the stratosphere. The water vapor injected into the stratosphere is very bad. It is not good, because it will destroy your ozone and many chemistry. And because water vapor in lower atmosphere, it may be few hours to 1 day, it may be there. But water vapor in stratosphere, it will be months. It may be, you may be heard about the volcanic eruption. If you happened, you heard about that volcanic eruption? Volcanic eruption. Heard or not? That because that this volcanic eruption is something different than a Pinato, because it was over the ocean. It was I think 20 degrees south and in ocean, and it has injected the volcano when it pumped. Earlier what happened, you might have a lot of aerosols and a lot of sulfur was injected in the stratosphere. This time what happened? A lot of water vapor when injected, we got the shock wave. In India also many they call it the shock wave of that one when it interrupted, and most of the water vapor is that come to the stratosphere. Now also some of the water vapor is still in the stratosphere, which is destroying the ozone. So this is actually this type of thing. That's why I was telling that tropopause, that is only the barrier which is stopping that mixing of these two layers. These you can have a very high resolution with this radar system. That is what big. Otherwise, with radius only 2 times a day you can get. And then you can see this like a Kochi University radar when you operate. I was telling you, we operated like east, west, north, south, and you are having like you see the second panel like a Doppler. You can see that the positive and negative Dopplers are there, right? Means one is toward the radar, one is going away from. So you can have that, because your radar is working perfect or not. You can see this is a perfect mirror image, because when you radar scan, because your wind is moving one direction. So one time it is toward the radar, one time away the radar. These are all perfectly coming with this radar system. And you can see these different layers, small layers. These are all turbulent layer structures. This is from the Kochi University observation. And I was telling there are some time when a lot of convection is happening, this mirror image, you see both are in the same side, the mirror image field, it is happening. So what will happen? There is rotating up dot, down dot. Supposing that you might have seen in when you rotate a wheel, no, there will be a vortex. Like similar thing is happening in atmosphere, which you cannot see. But if your flight goes over those locations, then you are can rotate. But it is so in very high speed, it will penetrate and go because this is a very small portion. But these type of things are also observed. This is what I was telling. There is a methodology which you can detect the tropopause site. From here also, I think Sujit and Nitya also has detected the tropopause site with using this radar. And these are the cases where I am showing that I was telling you that air from the stratosphere can come down. So these are some observation like weakening of tropopause. This type of thing only you can do with the radar, not with the other thing. This when it becomes that the tropopause become weak, then when it becomes weak, then there will be a mixing can take place. So this type of thing, I'm not going detail in that thing because you cannot understand what exactly we did, but you can study this type of phenomena where it is directly applicable. And like during tropical cyclone, because this radar you can operate tropical cyclone, you can have the weakening of tropopause. Here you see there is no defined tropopause, but whereas the tropopause has come down and with a lot of like ozone air from the stratosphere that you can study with this type of radar system. And this is one ozone profiling I am just showing you to show that you see these are the ozone which I was telling you from stratosphere. You can see this is a height, and you can see it can come up to the surface ozone during the tropical cyclone time. So this is very dangerous. And this is a CloudSat picture because you will be doing this type of things. You see that when the this cloud can penetrate up to the tropopause, it will weaken the tropopause. So these are the study we did with radar system. Only radar system we can do that. Otherwise, with balloon you cannot do this type of study. This is over Antarctica, and one radar is there. I think it is under control of the Kochi University. Satishan is taking care of that one. You in Maitri Island, one radar is there from Sweden. So similar kind of radar, but there is a very small one. So there also we did a lot of study with stratosphere troposphere exchange because their tropopause is very low. The pole side tropopause is 8 kilometer, not like our 16 kilometer like our tropics. So there also many type of things that is not as a blizzard. Like we have a tropical cyclone storms, they have a blizzards and all. Suddenly like storm type of things will be there. So those type of study we can do with the radar system because radar you can operate. You cannot go out to launch the balloon, but you can operate the radar. And now with the Gadanki radar, actually this is one of the things like this radar operate when you operate the radar and when you launch a balloon. Suppose you want to launch a ozone sonding, it costs around 1.5 lakh rupees per ozone sonding. So that is a direct measurement of ozone. But indirectly you can have with the radar because less cost is there, cost effective, and you can see that there is the nuclear fission and missing process happening. So this is what we did with the radar with the Gadanki radar. And during the as I was telling you, that isotropic and anisotropic and KHI structure that is known as the below structure will be there. So this type of turbulence are very dangerous for the aviation. So this type of study you can do only with a clear eye. You cannot observe with the naked eye, or you cannot observe with the DWR, the radar type system which is with installed in the flight. But you see suddenly there will be a bulbing structure. Of course, this at 18 kilometer, but this type of things are occur at 4-5 kilometer. That's why your flight and all those things are having heavy turbulence. And during convection, whenever very strong convection is there, you see it is looking like you can see all the red color. So because that is a very highly turbulent time at the time, and it can go up to the tropopause. You can see very clearly blue line and red line. It is very much distance between these two lines. Okay, but you see during the normal condition, you see all the blue because it is a high calm condition. At that time, nothing will be happening. So this is calm condition. But when it comes to a turbulent, you can see that highly red color things. That is actually you can observe with the radar. And like vertical velocity, all these weather phenomena, what is happening? Because you know about that is zonal and meridional. That is what actually we are measuring. But all the weather phenomena is happening because of your vertical velocity. Because when your air parcel start going up, then only you get moisture and your cloud formation. You require a CCN and all those things. That is different. But you first should have some air partial should go up. So the vertical velocity is one of the important parameters. That is what actually directly measure from this radar system. And here I wanted to present that even from Kochi University or from Gandhi, we try to compare this vertical velocity from the reanalysis data. Reanalysis data means the data which is assimilated and kept like in you will be having that one, or the balloon have some indirect method of calculating the vertical velocity, but it never matches the radar. But radar is not giving wrong. It is not wrong. Radar can give you see that only the direction is matching, but it never matches that one. That's why we require an observation. Any modeling, whether you are doing the WRM model or the analysis, it will not match. But you, with the radar, you can get the vertical velocity measurement directly from there. So with this one, I think one more and waves, gravity waves. This is the last slide. So you can study the gravity waves because what will happen? The energy and momentum, which is transport from the one, because energy and momentum will be transported, but the particle, the parcel itself will not go. It will just transfer the energy one to another, another to another. So this type of gravity of structure you can see in the radar. Why we require radar? Because this type of high resolution measurement you may not be getting every 5 minutes. You cannot launch balloon. It is very expensive and it is not practically possible. But this radar you can get every 5 minutes, 3 to 5 minutes. You can get the wind information. From there, you can extract the gravity because this is the way it is all your atmospheric circulation. Everything is depending on your wave because you know that ozone is more forming over the over our tropics. But most of the things we are not worried about much about the pole ozone hole or something because the tropics is producing, but it will transport. That is the bigger ocean circulation. So it will transport. So all the circulation will be affected by this type of short scale to the planetary waves. All waves this you can see that you can see very beautifully, you know, negative, positive, you can see. So these are the waves. So you can have that waves type of study, and you can see the phase propagation very nicely. All those things you can study with the radar. Okay, so with this one, I conclude. So there are many studies we have done with the radar system over here and Gadanki and Calcutta and all. So, but it will not be good to show the result. But I wanted to say that this radar, what you are having over here, you are having the excellent capability, and you can have many observations starting from the boundary layer. I am not showing boundary layer study. Boundary layer to the mesospheric height, if we are getting the signal. Otherwise, lower atmosphere, everything you can study with this radar system, and you are sitting in the place where your entry of the monsoon is there. You have a very strong LLJ, you have a very strong TJ, and these two are the things which do many changes in the atmosphere. Because now many people will be claiming that LLJ is decreasing, many people are claiming that LLJ intensity is increasing. So many things are there. But you have, if you have a long-term data over this location continuously, you can see many things are happening over this region, this tropical region. And ionospheric also, the person who is interested in ionosphere, in the upper atmosphere and all, that also very nice signal. Rakesh was doing, he was getting very nice signal that one. Then I think Honga Tonga also one paper has come from here, right? There also that it has come, impact is there. So that was many things are there, and geomagnetic storm, impact of geomagnetic storm. And actually one radar to be there in our equator region, like in Kumba, that is where I belong to that. That is a place where you are having exactly the ionized layer, what I was talking about, that how the radar started and all, the ionized layer was there. And rest of the lower atmosphere we can have a study. So I think this radar is uninterruptedly working, and now all other radars are there, and more 9 will be coming. So it is a best opportunity. There are very few people working in the radar. Very frankly speaking, very few people. Only Kochi University is actively doing that one. Any other 1 or 2% are doing it in lower atmosphere. I know they are doing, but lower atmosphere are doing. And this should be used and make then otherwise the expertise will be very slow, very going down. So many I was welcoming anybody interested to work with this radar system. You have a data, if any doubt is there, and SPL encourage students. There is I think student exchange programs are there. People can come to SPL, stay for 1 month or something. Any RL also they can stay. And then many time we'll be also coming here. So any doubts or anything, or anybody is interested in working on that radars, because otherwise many radars are there, but very few people are working for their thesis. So people can utilize this opportunity excellently. That is what actually I want to give a glance that this can work. This I have only 10% of work that Allah will be doing. But the concept and all other many things are there. These are the things what I am saying. We can have that one, and our engineering backgrounds are also very good. So they can also help you with the signal processing. Because signal processing we have up to certain limitation. The scientists have certain limitation up to this much I can do. Beyond that, some engineer can do, like Rakesh is present, this thing that we can change this thing, so we can do that many things. So this one I am concluding. Thank you so much here. Any doubt you can ask me or you can send me mail, so there is no problem. And you can conduct experiment and start seeing also. Sometimes you can sit. Actually, you have to sit in front of radar, then only you will enjoy it. Otherwise, it is like a satellite thing. Download data. I am working in satellite. I am working in rocket. And but I feel happy when I am working in radar. Mostly I am working satellite. But when I feel happy when I am working in radar, because when I was sitting here, I was telling Avilas that during our research time also used to sit in front of that. You can see the field, you might have seen the convection going, but you can see the air parcel going like this. You can see in the radar. Yes, you can one signal when you are going, you feel that you are going along the system. So you will enjoy when you sit in front of the computer. Not only satellite data will be there because none of the satellite is known to you, right? We can see only this photograph that this is a satellite. I am having these parameters. I am having whether cloud side or something or whatever. But when you sit in the radar, then you feel the difficulty, how it is difficult to work with the radar system. Okay, thank you.